In this video, we solve problem 4.7.16 from Nagle's Fundamentals of Differential Equations with Boundary Value Problems, 7th edition. We're asked to find the general solution to the given equation for t less than 0. Now, I'd like you to notice that the power of t and the order of the derivative multiplying it are the same. We've got a t squared and a y double prime, a t to the first and a y prime, and there are no t's here and a 0th derivative. So that makes this a Cauchy Euler differential equation, and it's homogeneous. So that means, and it's second order. So that means the solution is C1, general solution is C1y1 plus C2y2, and y1 and y2 can be found by letting y equal t to the mth power. That's the form of the solution of a Cauchy Euler equation. So we will take the first and second derivative of this, and then we'll substitute into the equation and see what values of m would cause t to the m to work for this particular Cauchy Euler equation. When you take the derivative, you just use the power rule. So you bring the power down and multiply by t to the 1 less power. Bring your constant down, then bring your power down, then multiply by t to the 1 less power. If you want, you can distribute that m through the parentheses. And then you've got t squared times y double prime, you're substituting into the equation now, minus 9t times y prime, which is this m times t to the m minus 1. And then we're adding 30 times y, which is t to the m. We add all those together, we have to get 0. Now, the only way that happens is if this equals 0. Now, in order to find the values of m that make this true, we need to factor it. We need to write this as simply as possible. So I'm going to combine, the powers of t that are multiplying each other. Remember, if you've got t to some power times t to a different power, you just add the exponents, because that means you've got 2 copies of these over here, and you've got m minus 2 copies of those over there. So how many copies of t do you have? Well, you have this many plus that many. And in this case, that's going to be a t to the m. M minus 2 plus 2 is m. And here, similarly, m minus 1 plus 1 is m. And here we've got a t to the m as well. Because of the relationship between the powers of t and the orders of the derivative, there will always be a factor of t to the m if the Cauchy Euler differential equation is written in this form. So if you factor out the t to the m, you're left with m squared minus m for this first expression, and then a negative 9m for the second expression, and a 30 for the last one. And we're saying this times this equals 0, but t is strictly greater than 0, or strictly less than 0, excuse me. So this is never 0, so that means our polynomial must be 0. So we must have m squared minus 10m plus 30 equals 0. Now, I can't think of 2 numbers that multiply to give me 30 that add to negative 10, but I see that that coefficient of m is even, so I would recommend completing the square. Now, some people might prefer to use the quadratic formula. I just prefer to complete the square. So what I would do is I'd leave these guys on this side, subtract the 30 from both sides in preparation for completing the square. There's a coefficient of 1 here, and there is. The number in front of the m is called b. You want to take half that, negative 5, and then you're going to square it. Negative 5 times negative 5 is positive 25. That's what you add to make that side a perfect square. And that's legal as long as you add the same thing to the other side. Then we want to write this as a perfect square, and then of course we want to simplify the right-hand side. M minus 5 squared turns out to be equal to m squared minus 10m plus 25. So you're asking yourself, what 2 numbers multiply to give me 25 that add to negative 10? It's going to be negative 5 and negative 5. Turns out to always equal this, this number right here, the b over 2. So we're going to have m minus 5 squared, and that will equal this negative 30 plus 25, which is negative 5. Okay, now we're trying to get m by itself, so we'll take the square root of both sides. Don't forget the plus or minus on the right. because you can have a positive number or a negative number squared to get this perfect square. And so we end up with plus or minus square root of 5. And since there's a negative under the radical, that's going to be an I. So when I add 5 to both sides, I have 5 plus or minus the square root of 5i. And that is a complex conjugate pair. So that's my M1 and my M2. So this is alpha plus or minus beta I. Alpha is the real part, so alpha is 5. And beta is the imaginary part, but you ignore this sign. Beta is always positive, but beta is positive square root of 5. Now, since we have complex conjugate roots, our solutions involve sine and cosine, but remember you are working with a Cauchy Euler differential equation this time, and not a first order linear equation. So remember y1 and y2 for complex conjugate roots are going to give us, are going to be t to the real part times cosine of beta times natural log of t generally. And the second solution is going to look just like it, but instead of a cosine, you have a sine. But I want you to remember what they said at the beginning. They said for t less than 0. That means we can't have a natural log of t here. If t is less than 0, that means t is a negative number. In order to put a positive number inside the logarithm, I need to take this t and multiply it by a -1. So this is going to be a negative t here and here whenever our t is less than 0. Because it'll be a negative times a negative will be a positive, and you can take the logarithm of that positive number. Okay, so those are the forms of our solutions for the corresponding linearly independent solutions for complex conjugate roots in a Cauchy Euler equation. And in our case, alpha is 5 and beta is square root of 5. And because of this domain, which was given to us at the beginning, we've got the negative t inside the logarithm rather than the positive t. Okay, so what did we do? We found our characteristic equation, and then we solved for M1 and M2. And if you wanted, you could have used the quadratic formula. That would have been totally fine, and you would have ended up with the same values for M1 and M2. And once you have M1 and M2, we need to find the forms of Y1 and Y2. Then the general solution is C1Y1 plus C2Y2 on the interval from -∞ to 0, since t is negative. So we have C1 times t to the 5th times cosine of square root of 5 times natural log of -t plus C2 times t to the 5th times sine of the same thing on -∞ to 0 where t is negative, excuse me. And that's it.